لا حول ولا قوة. يا الله. Assalamu alaikum. Do you have questions from last time? Questions, comments? No? Have you downloaded everything for what is recorded? Okay, I think that Teams will start deleting, okay, some of the content, okay? So download it on your local machine to have it there. About the grades, is there anything missing on the Blackboard to grade? Homework 2 is done? No, the grades of homework 2 submitted? So the grades have been posted. Engineer Amit corrected homework 2. Okay, good. That's good. And he posted the key. Sounds good. Okay. So we said that we will have a quiz after we come back, right? Okay, good. So today's lecture is not included in that quiz, right? Today's lecture is not included. Good. So let's make a small review. Yes. Homework 2 is not posted, the grade? شو يعني for all or no? I will talk to Engineer Ahmed. He is the one in charge to correct the homework. Okay, good. The key has been posted at least. أنا أعطيته الكي من زمان لأني. Okay. Let's make a small review of what we saw, okay, and along this chapter. So we said that our concern is to increase the data rate. Among the 3 parameters, we selected the bandwidth, but whenever we selected the bandwidth, our channel become impossible, okay? So it became a frequency selective channel that is non-equalizable. To deal with that, we need to do frequency slicing, which is OFDM. Good? So that motivated OFDM. We commented on OFDM. What is the difference between OFDM and FDM? Okay. We said that mainly it is an overlap, a smart overlap. It is an overlap without interference that we have. So here you see they will overlap, but in a smart way. And this overlap in a smart way will give us double the data rate or double the number of customers or a 50% saving on the bandwidth. Last time also we started with the RF up unit. So we said that in order to make the signal to move to the desired frequency of Wi-Fi, Bluetooth, or whatever, we need this unit to be what we call RF. So as you see here, all the processing is on the baseband. And then at this last unit, we take the signal to the RF. Good? Usually after taking the signal to the RF, we do nothing. We directly put the antenna, okay? Otherwise, we will have losses here. Good. So they follow this approach. Khalid, what are you doing? تعال, please. So with this RF unit, how we can put the signal on a specific frequency? We multiply by the operating frequency like this. Okay, where here the omega is the 2 pi f. Good. So the frequency that we need is here. We put it inside the cosine and sine, then the signal will propagate. And this is how we do RF. It could be plus or minus. Both options is good. Good. So this is how we do it on, let's say, a traditional, okay, old system. So how to do it on OFDMA? First question, what is the operating frequency in OFDM? Abdul Ghani, what is the operating frequency in OFDM? Hisham? منين جبت هذا الرقم؟ So, range of frequencies. Very good. So it's not one single frequency. There are several of these frequencies. So whenever here we, instead of one frequency, we have several of them, what we have to do? Several of this operation. Good. So here, this is why in OFDM, we don't have one single frequency. We have frequency 1, frequency 2, frequency n. Okay. So we have to do this. It's called carrier loading. Okay. So we have to put the signal on this frequency, on this other frequency, and so on. The idea here is that the symbols that will come, where can I write? Okay. Imagine that here it's an image with pixels. Here, how many? 4, 5, 20 pixels. Imagine that we have 20 pixels. Okay. If it is a traditional system here, traditional system, we will send the first, then the second, then the third, then the fourth, then fifth. Okay, so here, if this is time 1, time 2, time 3, time 4, time 5, this will be how we will transmit the symbols. Okay, so we will take the first pixel, we will transmit, then the second pixel, then the third pixel, fourth pixel, and at the receiver, they will be ordered so that you see the image. Good? How we will do it in OFDM? We don't have only one frequency, we have several of these frequencies. So what to do? We will take the first, second, third, fourth, let's say how many here? OFDM of n equals 8. 2, 3, 4. So we will take at T1, we will transmit 1, 2, 3, 4, 5, 6, 7, 8. At T2, 9, 10, 11, and so on. So here now, instead of transmitting only one, we transmit several of them, each one on its frequency. Why I feel you're sleeping? Enter mainly. You follow us? You follow us? Hisham? Yes. ايميل الكاب هاي بليز. لفها على العكس عشان اشوف وجهك. يا بتقيمها يا بتلفها، شو بدها؟ لا كده احسن. يا بتقيمها يا بتلفها يا بتغير القاعة، شو بدها؟ لف بس هيك اعمل هيك لورا. كده. I need to see your face. لا أنا I don't see it. طيب اوكي ارفع ثاني اشوف شوي. I can see you. أيوه. Oh, very nice. Okay, good. So what is the feeling whenever you are using OFDM? What will happen? Hani, what will happen? Times of anything. Okay, whenever you are using OFDM, so what will happen compared to the traditional? So instead of you needing 30, how much here? 20 pixels. So 20 time instance. So okay, now you will need how much? 2.5. Okay, so the system is faster. Your data rate will be much better. Okay, so whenever you download an image, it will take much less to be downloaded, image or video or whatever. Clear? Hani. Okay, so here this is the idea. So here now, instead of sending each one separately, we will send the first, the second, the third, the fourth all together. Okay, this is how we feel the system to be faster. Good. Here, this is the operation that is carried out here. Okay. We need this unit. Even here is written SP, which stands for serial to parallel from digital embedded systems. Okay. So here we have the sequence comes like this: S1, S2, S3, S4. So here This one, it was telling you that we will S1, O2, O3, O4, O8, or 100, okay, they will be transferred to be together. So from a series sequence into a parallel sequence. طب how this is done in software? Because here the system is software. How this would you think that it will be done on a software? If you want to program this one, Abdul Ghani. Ali, we need a code, so it will transform symbols that will come series into symbols that will come in parallel. How to do this? A for loop. So here a for loop will do it for you. So this is why I say it is pure programming. Okay, pure code writing. Is there any chance in a few students in the other class? Good. So we have here this for loop. After we do it, okay, so here we will have, how much is the n? Do you remember what is the typical value for n? Hamid. N. No. In a practical system. No. An example, Wi-Fi or 4G. 64 for Wi-Fi, 512 here for 4G. At least in Qatar, okay? Well, many countries in the world. They have a Wi-Fi, 4G system with 512 subcarriers. Good. So here, now that we want to transmit, imagine 512 subcarriers. So how many antennas that your mobile phone has? In the best cases, most probably two. So how then to transmit 512 frequencies over two antennas? This is why we have to put them back again together. So here, this unit is simply an adder, okay, that will add each one of these, okay, and then they are sent. If we look here at the output of the adder and the time domain, what we will see the signals overlapping on each other, okay, undistinguishable, okay. If we look to them in the frequency domain, how they will look like? That's it, different frequency, because each one of is on a different frequency. So the signal here, it will look like this one. So here we will have symbol 1, symbol 2, symbol 3, symbol 4, symbol 5, and so on. So on the frequency domain, they are perfect. Okay. On the time domain, they are completely overlapping. Good. But yeah, if in one domain they are fine, we can distinguish between them. And then there is this unit that I will explain by hopefully by the end of the lecture we will reach. Good. Clear so far? Okay. How to make this adder? Another for loop. So here another for loop to add them. So software. Don't tell Allah, I need to go to Ayman's office to search for an adder over the 741. No, here software based. Good. By the way, question: have you used the software on ChatGPT? Have you asked for a programming something? But yeah, it gives you yeah, definitely it's still it's iterating, it's learning. مسكين خليه شوي بتعلم. Good. Okay, so then here this signal, whenever it's added up, it will look like this one, which mean here the first symbol you see here, Sn, multiplied by e to the j omega t, Okay, and from, well, n equal 1 to n, or from equals 0 to n minus 1. And now my question, is it familiar to you, this expression from previous courses? Khalid. Laplace, no, Laplace, no, fish frequency, PS. Fourier. So here, this is the Fourier transform expression. Good. Question 2. Shab. Only 12 students. Is there an exam today? Sure. Control. midterm control. انا مش فاهم كيف midterm يعني. عندنا midterm حق الإجازة. Really? Shab. What was the question? Okay. What is the Fourier transform for? Why you will need the Fourier transform? Good. Or it has the inverse one. So, and why you need to transform the signal from time domain to frequency domain? Because frequency domain is easier to work with. No. Why we need to go to see what's happening on the frequency domain? And see the signal better, understand. To see it better, no, but yeah, to understand more stuff. Okay, so we as engineers, well, electrical engineers, is not enough for us to see what's happening with the signal in the time domain. We must see what's happening on the signal in the time domain and frequency domain. If you are a power engineer, you need to see hysteresis, okay, of the motor, okay. How would we have the motor? All of that is seen on the frequency. You are a communication engineer. Okay, you need to see how the signal propagates. You are a biomedical engineer. You need to see the ECG signal and so on. So every time, it is not enough for you to see what's only happening on the time domain and frequency domain. And what is your tool? The Fourier. So the Fourier is our tool to see what's happening on the frequency domain, or if the signal is in frequency, see what's happening in the time. Sometimes, and yeah, this is why Shab, okay, made this comment. Sometimes the signal in time domain is not easy to deal with. So hopefully we move it to the frequency and it will be easier. Sometimes to deal with the signal on the frequency domain is not easy. So maybe whenever we will to move it to the time domain, hopefully it will be easier to deal with. Good? Clear? Clear, Isham? Fine. You commented Laplace. What is better, Laplace or Fourier? Why? Good comment. Okay, so the Fourier transform is a kind of Laplace transform, but Fourier transform is more useful. Because Fourier transform will tell you what's happening on the frequency. Laplace, it is kind of frequency. You remember this S, which is sigma plus j omega. So it has the omega, but yani, let's say a complex function. Whenever Fourier is not there, Laplace will yani, instead of saying, well, la hawla wa la quwwata, there is nothing. Okay, at least we will have Laplace. But as long as Fourier is there, no, you always use Fourier. Good? Clear? Hisham? Clear? Okay. So, how to use the Fourier? Have you ever implemented the Fourier transform? MATLAB, okay? In MATLAB, there is a function called DFT. Discrete Fourier transform. You will put the signal. It will show you how it is its Fourier, okay? How is it on the frequency domain? Good. The issue, whenever you would like to implement the Fourier, is that it is complex. The number of multiplications and additions that it needs on the processors are a lot. And if they are a lot, what will happen? But well, depending on the processor, maybe it is slower, but yeah, it will consume more electricity, it will generate more heat, all blah 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 stories of more complexity. This is why they came up with something better than the Fourier called fast Fourier. FFT. What is this F of T? You have seen it in signal system, right? Sorry? In signal analysis? In signal analysis also, but yeah, in يلا كويس. You are taking in signal analysis this course? Who's teaching? And you saw F of T. What is the difference between F of T and DFT then?
This one is much faster
than اسمه fast. What is better, the DFT or the F of T? F of T? طب هو fast يعني there is nothing for free. No. بدون نوتس هلا فكر معي. What is the disadvantage? Which is continue. هشام. We said it is less complex and fast. Limitation on what? فيش hardware, software. Limitation on signal. مش كل السيجنال بصير عليه. No. طيب. F of T, it is not an approximation. It is exactly the same as the DFT. So again, it is fast or showing exactly 100% the same performance. Okay. This is a common question, interview question. Okay. They want to ask you technical. Difference between DFT or F of T. Okay. Or what is the Fourier transform used for? Actually, here in the department, whenever we interview students who want to go with masters, this is a usual question. Why you use the Fourier transform? Good. If you want to continue with master, yes, there is an interview. We ask you technical questions. Or sometimes Dr. Sarkan give you an equation. Okay, and he has to analyze the equation. But yeah, and any, let's say, reputable university, if you want to continue graduate studies, yes, they will make an entry exam. Okay, so then here the DFT and the F of T again, they are exactly the same, not an approximation, 100 perfect. Okay, the F of T. If and only if, okay, there is a constraint. If you want to use the F of T, that the n has to be equal to the x. So let's say this is a kind of restriction on the input signal. Okay, so if you want to use F of T, your signal has to be 2 to the x. Does it sound familiar to you? Ali, does it ring the bell on something that you have seen? Ali. No? Khalid. No? Shab. Where in source encoding? طيب, where we saw 2 to the x? If it was 2 to the power of x, we could just use this command. We did not need the Hoffman coding. They both give the same performance. How much you got on the midterm? Can be reduced, huh? Be careful. Khalid. Omar, where have we seen 2 to the x? Today. So here, it's written here. So here, whenever we saw the n, I'm sure I wrote it here. Where is the n? I wrote it. شكله لا. في سادات راحوا؟ عن جد؟ لا 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 لا.
مش موجود في الريكورد بتاع
اوكي والله صار في عندي كوريوستي اشوف معقولة مش كده. واي فاي و LTE و so on. Whatever. Good. So here the n of subcarriers, the number of subcarriers n. Okay, we said, and you can check the recording. لا, no records here. It's here. 2 to the x. So here the number of subcarriers, okay, is always 2 to the x. Okay, in practical systems. Why? Because in practical systems, they will always and always use f of t. They will never implement DFT. Never. I've never seen a system that implements DFT. Okay, they always go for f of t. Okay, so they will make 2 to the x. So imagine that your signal is not 2 to the x. DFT is never implemented in practical systems. Your signal is not 2 to the x. What to do? That's it. Increase it. How? Let's say, imagine that you have a signal of 100 symbols or samples. Is it 2 to the x? Right. What is the next 2 to the x? 120. Well, let's see. A good example. I put it some years ago as a question. You have two options 2 to the x. This is 2 to the 6, right? This is 2 to the 7. I'm right? 2 to the 6, yeah? Yeah, it is. Okay, good. So, these 100 symbols, okay, they are not 2 to the x. We need to make them 2 to the x. Which option you will select? Option A or option B? Very good answer. That usually it is, but here it is not. Ahmed. Why?
because it's near to the power, near to our sample.
Hamad, A or B, and why?
B, because you said we need to increase.
Hisham. Why? Perfect. So here, if you go from here to, yeah, it is close, okay, but if you go to this one, you will have a 6 symbols lost. Okay? Yeah, so here, we will not go here because we will have lost. What will happen whenever we go from here to here? There is an operation called, I have not explained, but yeah, it's called zero filling. In the standard, they call it zero padding. Zero padding with 1D or 2Ds. Zero padding. What is zero padding? What does it mean to pad? Yeah, to fit. So here, zero padding or zero filling. What is the story? So it's say you have 70 symbols. Okay, it is much better that you add 30, 40, 58 zeros that are useless. Okay, but this way you will reach 128 so that you can use the f of t. I repeat, your signal, this is your signal, 70 symbols. What to do? Okay, so whenever it is 70 symbols, you need to use f of t because this one is never used in a practical system. Good? So you check the 2 to the x, even you have 64 or 128. If you go to the 64, you will have here 6 symbols lost. Simply lost. Good? So here, then this is not a good approach. So what to do? They said, okay, let's go to 128. Here, from here to here, we have 58 empty. Okay. So what to do with these empty? We will put zeros, even we don't need them. Okay. We will put 58 zeros. We will say to the receiver, hey, receiver, from 71 to 128, they are useless. Okay. Don't even decode them, but they have to be there because la hawla wa la quwwa, we have to use f of t. Good. This way, the system will still use f of t because yes or yes, we have to use it. And then we make this to be 2 to the something by this zero filling. Hamad.
So if we have 70 symbols of 120, it will use 128.
That's it.
But in 120, it will be better because we will add only 8. Or...
It will be the same because here the same complexity is there. So if your signal is 70 or 127, it is exactly the same complexity. You have to put the f of t of 128. Okay. With the first one, you have to fill more zeros, but yeah, it is. You will say to the receiver, "Hey, receiver, the last 40 zeros, forget about them. The last 2 zeros, forget about them." Okay, but you have to use the f of t. So they will be the same. Hamza, same question. Someone else was raising hand. Abdul Ghani. Clear this point? So again, conclusion, we will always and always deploy f of t. It does not depend on the application. It has to be always f of t. Clear this point? Omar. Okay. So then in a practical system, this setup will be, where is it? Like, okay, so we have, well, software. I will discuss. Let me put here later. Good so far? Sure. Then, what is the basic of communication? Whatever you do at the transmitter, what you have to do then at the receiver? That's it. You have to inverse. Whatever you do at the transmitter, you have to revert it at the receiver side. Now let's see what at the receiver side. What is the procedure? Let's go first of all to a traditional system. Where is the traditional system? I erased the traditional system. In a traditional system, we have the symbol, then it is multiplied by e to the minus j omega t. Then we have the antenna, right? At the receiver side, we have the antenna. The first, so this is the RF up. So here it was baseband, no frequency. Then we increase it to the desired frequency that is inside here, right? Then here at the receiver side, what is the first unit? RF down here, RF down. The signal from here to here will travel at the desired frequency. Whenever we want to process it, we want here to be at the baseband again, so we can deal with it. Good? Clear, Abdul Ghani? Sure? How to do this RF down? If, for example, here we have the signal, we multiply by e to the minus j omega t, then we multiply by e to the plus j omega t. What will happen? They will cancel each other, then it's equal to 1. This is why here at the RF down, okay, the unit here, it will be u multiplied by e to the plus j omega t. And this is why I told you before that it could be a plus or minus, because if here you make it plus, here you will make it minus. The objective is that the signal comes to here, you increase on the frequency, it flies, it is detected, then you remove the frequency, achieving that this is equal to 1. Clear? So here, this is the RF down. Question on this traditional system?
How the receiver will know the frequency?
Yeah, for sure. Here the system has to tell you, okay, what is your operating frequency. So whenever your phone connects to the network of Ooredoo or Vodafone, okay, the network will tell the phone that you are operating on this frequency or frequencies, more than one. The same whenever you connect to Wi-Fi, okay, the system will tell you this is your operating frequency. Good, Hamad? You follow us? Sure. Thank. What will be different, Hamad, on OFDM? Hani, in OFDM. Okay, but subbands, keyword. Okay, so here we don't have one single frequency at the receiver side. We have several frequencies. This is why at the transfer we didn't do here one RF up, several RF up. Good. So here what do I have to do at the receiver? Several RF down. So here at the receiver, first of all, this is the one that I will explain later. Okay, then serial to parallel. So the whole signal that will come distributed over symbol 1, symbol 2, symbol 3. Each one of them multiplied by the it's called deloading. Okay, so we take the signal from high frequencies to low frequencies, and after that, demultiplexing, demodulation, source decoding, blah blah blah, coding, and all the operations of the decoder. Good. This operation here, this is what is different. Okay, so we don't make a signal to go down from the operating frequency. It is operating frequencies, more than one. This operation here in a practical system is the I f of t, which is logical. If we implemented f of t at the transistor, we will put I f of t at the receiver. Cool, clear, questions? Sure. Khaled. Kia. Also here, you could use the I f of t at the transmitter and make f of t at the receiver, as long as they reverse each other, depending if you are looking to a signal on the time or frequency. Okay. Questions? I forgot your name. Shihab, yes. Shihab. You follow us? You look to be sleeping. Kian? Very good. Let's come to this one. So how many subcarriers do we have in a practical system? You go to CRA. Assalamu alaikum, alaikum assalam. I want a band. How much do we have? Wallah, we have 10 megahertz. You have to make calculations. This 10 megahertz. How many subcarriers they will give you? This is what we do. Okay, so here we divide them by 15 kilohertz. Where this 15 kilohertz came from? Okay, LTE, 4G. But why it is 15 kilohertz? Why they decided to make it 15 kilohertz? No? Yes, we know. We are learning, understand what they did, so that in case whenever they hire us at Ooredoo or Ministry of Energy and they ask us to do this change, do that change, we know where to go and dig in. No?
Okay, so 4G is 526.
512.
512.
But no, not that. Today's lecture is frustrating يعني. والطلاب موجودين نايمين. نايمين ولا مش نايمين يا خالد؟ انت اكتب اذا انت نايم كويس. طيب. We said that the channel will be like this, okay, between frequency 1 and frequency 2. Can we equalize this channel? If we slice only. How many slices we do based on what? You were not here in the last 3 weeks, huh? 1 week. طب okay, good. You saw the lectures? يعني ما شفتهاش. يعني شو عايش شفتي قاعد. Okay, good. Hisham. Based on what you will make the slices? Hisham, go ahead. Based on what you will make the slices? Why we slice? To have subcarriers. So here we make subcarrier so that on each subcarrier here the performance is the same, or we can approximate it to be the same. We say here on each one of these the performance is the same, so we can equalize, and so on. So then, how to know how much the frequency performance will be the same? What is that named? We already studied it. Coherence bandwidth. This is called coherence bandwidth. So here, the coherence bandwidth is how much the band that we can consider to be fixed. Then here, this is the how much the band, this is the coherence bandwidth, a bit less. I will explain now. Okay, how to know how much is the coherence bandwidth? They have to do test trials. What they did here in Qatar, for example, they hired Karwa. Okay, they got cars from Karwa. They put a transceiver on the car. Okay, and then they say, go ahead. Okay, they were working for 1 month. After the month is over, they called the cars. They collected this unit. They took the information and they checked. Okay, they made statistic how frequent the channel changes, then how much we can consider the channel to be fixed. Doha, LA, Paris, whatever cities, some of them Khalid hot, okay, some of them cold, some of them mountain, some of them next to the sea level, okay, so that they see on average how much is the coherence bandwidth worldwide, because they will not make phones only for Doha or phones for the States and so on. Good. Based on that, they saw that the value that guarantees the phone to work on any place you will go is this value. Most probably the value of the coherence bandwidth should be maybe 21, 22 kilohertz. But yeah, to be on the safe side, they put it 15. Clear? So this value is, they made the calculation of the coherence bandwidth. Then after that, they checked with the test trials. Good. So here you go to CRA. This is the total band. You'll say divided by 15 kilohertz. I make the calculations. I know how much sub-carriers I can obtain. Clear? 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 Okay. This equation has a mistake on purpose. I put this, there is something wrong on this equation. And the one who finds out what's wrong, I will give him a bonus. What's wrong on this equation? Based on whatever we have seen. It will be 2 to the power x. If not, we will make it 0 padding. What's wrong with this equation based on what we have learned in this chapter? Khalid, Shah, no? Hint? We commented about it today. And you don't need to تفتيش and stuff. I think we commented, yeah. Yeah. Hani. No one? Today in the review, I commented that if it is an FDMA standard system, this is what you will do. Total band, 10 megahertz. Each one of them, how much? 15 kilohertz. You will do what? You will get the number of N. But in OFDM, that's it. Okay, so in OFDM here, they overlap in a smart way, smart engineering way. We make them to overlap, but without interfering between each other. So here, instead, wherever we have fit for 10, we will put here, we will fit them with more. Let's say here in red. Come on. And we will put more of these, reaching a 50% bandwidth saving, or double the data rate, or double the number of customers. That's it. This is why here, this equation, in theory, it should be multiplying 2. Clear? So for OFDM, okay, you should multiply 2. This is in theory. In practice, this is a bit less. So this is in theory. Well, first of all, fix it, because I put it on purpose, okay, on the slide. So this equation is wrong. Theory. So whenever it is in a practical system, this 2, instead of 2, it is 1.98, 1.95. Why do you think that? No.
عصبة.
أعطيه بوناس؟
عصب عليه.
لا حبيبنا هو ما كان.
لا فعلا احنا ما عندنا 10 ميجا هرتز.
We have. طيب. Why we let's see here. So how many black do we have on this band? 10. Good. How many red I can fit? That 1, 2, 3, 4, 5, 6, 7, 8, 9. Why of that? Because here on the edge I cannot fit. Here on the edge I cannot fit. This is why it is not directly multiplying 2, but a bit less than 2. So in a practical system, well, depends on how it is 10 or 100. So yeah, it could be something less. It could never be more than 2, but yeah, it could be a bit less than 2. And this factor is called OFDM expansion factor. Remember it whenever we will design the whole network. After whenever we will finish all the parameters, we will take it into consideration. Cool. It's a must in OFDM. Okay, if it's not there, or if the value is 1, then it's not OFDM. It is FDM. Okay. Questions? Omar, raising hand. Raising hand. No questions? Okay, we will stop today. No need for more.